Yeah, so before we continue, let's talk a little bit about the history of the polyhedral model and the polyhedral compilation and so on. And there were actually, in my opinion, a few very, very early papers that set the stage. They didn't do sort of polyhedral compilation or polyhedral model, but there was a paper in 1967, which is sort of the heart of everything, which is by Karpmiller and Vinograd in the Journal of the ACM. And that is a very difficult paper to read, very mathematical, but if you have the chance, please go and read it. Please read it multiple times, because I have found over the course of the last 35, 36 years or more, that every time I read it carefully, I see some new things. So about 4 years ago, I discovered that actually some of the ideas about scheduling, even in the presence of cyclic dependencies, are there in that paper. So you can still find schedules for programs even though they have cyclic dependencies. Cyclic dependencies, something depends on something, and you have a cycle, which means that there is no timestamp that you can say that one precedes the other, right? So in a system of equations, scheduling is, you basically say this program does not admit a schedule when there is a cycle. However, some partial results are in that paper, and I discovered them, more or less recently, 4 or 5 years ago or so. So please take a look at that paper if you get a chance. The next important paper, in my opinion, is Leslie Lamport's paper in 1974, which is, the title is, it was in the Communications of the ACM, not Journal of the ACM, 1974 Communications of the ACM. And it has a very simple title, Parallel Execution of Do Loops. It too is a very difficult paper to read, but a large part of the difficulty here is because the paper is not very well written. There are very interesting ideas. He talks about programs that are a restricted kind of the ACS that we saw today. And he shows that in some of them, in some situations, you can do array data flow analysis relatively easily. So you don't need the machinery that we talked about, which was invented by Fautrier in 89. Then in the 80s, we started looking at things called systolic arrays, which is a class of parallel hardware architectures for VLSI that has local communication, nearest neighbor, and so on. And it is a target architecture that is in this new era of convolutional neural nets and machine learning, etc. This is coming up over and over again. So it's becoming popular. But of course, the version that we see today is different from what we were looking at that time. And the big problem that we wanted to solve was how to map a program into these parallel hardware, into these parallel circuits. And that is when we started looking at systems of recurrence equations. And there were some nice papers by Patrice Canton and a number of others. Robert Kuhn's thesis from Illinois in 1979, I believe, also set some of the very early results along these lines. And it was basically looking at something that we just saw at the end of the last session, where you have a computation which has these nice uniform dependencies. And by uniform, what I mean is that any node ij depends on another node that is a constant vector away. Okay. So we saw the north neighbor and west neighbor. That is 0, 1, and 1, 0 are the dependence vectors, or -0, -1, and -1, 0. Okay. So those kinds of computations, people started developing schedules for started figuring out how to do parallelization. And you will see actually some of those when we talk with today's examples, because our today's examples are simple. They use those results. They don't use sort of the more sophisticated results that came up later. And then, when I started looking at it, I wanted to look at computations that are richer than uniform, so that have programs that have linear or affine dependencies. Okay, something like we saw in the example, ij depends on I-1n, or ij depends on ii, for example. Okay, so the producer is some affine function of the consumer. Okay, but the affine function is not just consumer plus constant vector. And when we started looking at those, it turns out that scheduling problems become difficult, transformations become difficult, and so on. So that's when we started looking at it. And then I had a visit to France in Patrice's group in around '89, and many of these ideas were gelling together. And we were looking at how to take equations, how to parallelize them, and so on. And we were very, very confident that this technique that we were using to design parallel hardware circuits could also be used for compilation. So taking a loop program and then figuring out how to find schedules and so on. And although I was not there, there was a meeting between Patrice Quinton and Paul Fautrier, and that was, in their discussion, basically many of these ideas of polyhedral compilation were born. And then Fautrier wrote a sequence of actually 4 papers. Okay, and the order in which he wrote those papers is extremely important. The first paper he wrote was a tool called PIP, Parametric Integer Programming, which basically has this result that I talked about very briefly today, that if you take a polyhedral set and you seek its lexicographic max or lexicographic min, what you get is one of its vertices, but you can get it even when the domain, when the integer set that you're talking about is parametric, and it is a piecewise affine function of the parameters. Okay, so that was his first paper in 1988. Okay, then in 1989 he wrote this paper, which we talked about, which is array data flow analysis. And then a couple of years later, he had a sequence of 2 papers that showed how you could find schedules. It was a technique that was a dual of the technique that I had in my PhD dissertation. In my dissertation and in some of the early work with Patrice Quinton, we used the notion of vertices as a compact representation of polyhedra. And that gave us conditions on how to find a schedule when there are affine dependencies. Paul had an idea of using the dual representation, which is basically, instead of vertices, you think of the linear inequalities that define the polyhedron. And then he was able to extend or to adapt Farkas' lemma, which is a very well-known theorem in linear algebra, in linear programming. And he was able to show that you can have a set of constraints on the constrained representation of polyhedra and also solve the scheduling problem. And then his second paper was on multidimensional schedules. Okay, and so he had this series of papers, and the important paper that most people think about is really the 2 scheduling papers that came in '91. But he knew, he had this long-term vision over the course of 3 or 4 years that this is exactly how we should do polyhedral compilation. And he started off with, well, I first need a tool that does parametric integer programming. So it's a beautiful sequence of papers, and my admiration for his work is because over the course of 4 years he wrote these 4 seminal papers, and it was only after we at least read his last paper that said, oh, that's why he did that first paper 4 years ago. It was really beautiful reading these papers and reading them sort of in this historic context. So again, so he is in some ways the father of polyhedral compilation, because bringing these techniques to compilers was really his vision. We had some inklings that yes, it could be applied to compilers, but the main idea of bringing it to compilers was really multidimensional scheduling, and he had this vision. So I'll stop talking a little, about the history, but I think it is important, especially as this is being recorded, that the credit is given where it is due. And I'm sure I'm missing many other very, very important pieces, the work of Dart and Robert on scheduling and so on. But I, at least wanted to highlight these results. So remember where we were. We had a program. We had a program, and we had figured out the dependencies, and the dependencies were these constant vectors, 1, 0, 0, 1. In this example, it's a 2-dimensional iteration space. You have unit vectors as your dependencies, essentially, and we were able to figure out the schedule, right? So once you do that, we decided to transform the graph, or transform the program in such a way, and it is actually this transformation that I'm going to explain in a little bit more detail. Okay. Once you transform this graph, what used to be a rectangle becomes a parallelogram. What used to be vertical lines become oblique lines to go, oblique edges going to the northwest, and so on. But it is possible to construct an equivalent program representation, or an equivalent system of equations, because our program representation is the system of equations. You may think of this as a polyhedral set and a set of dependence functions. You may visualize it as a picture like I'm doing over here. All of these representations are the same, are in some sense equivalent. Okay. But after doing this transformation, then what we have done is to make the time axis perpendicular to the to the wavefronts. Okay. So all the points that are scheduled at the same time are going to be executed at one point along this time axis. Okay, and now we want to use our information about, we want to develop how to do the math so that we can do this as a program transformation. Okay, so you have a node ij. It is mapped to some new node p and t. T is a time step, and P is a virtual processor. Okay, and we call it virtual processor because the history of this thing was came from systolic arrays. So these were this aspect of the mapping was the processor. Okay, so the mapping is ij goes to I comma I plus j, where the first coordinate is P and the second coordinate is T. Okay. And the schedule is I plus j minus 1. Okay. This is done because my top left corner of my rectangle, my domain was 1, 1. So I plus j gives me 2, and I want to start my computation at t equals 1. So I plus j minus 1 is the affine function that tells me the timestamp. Okay. I am going to compute the inverse of this function, because this is going to be mathematically important. Okay, and it is basically pt goes to p, t minus p plus 1. Okay, How do you compute this function and or its inverse? You may want to look it up in the tutorial, but this is basically, if you go back and review linear algebra, you will get it. It's basically a matrix, the inverse of a matrix. Are people comfortable with this? Unfortunately, what has happened is that my camera with my pad, I forgot in my office, and I'm now doing this from home. So I'm not able to write down and show you things on paper. I apologize for that. And therefore, I want to be absolutely sure that I don't lose you guys when I give any explanation. Okay? So let me try to use the chat box. Maybe there is something that I can do over here. The mapping, and I'll use this notation, ij goes to j comma I plus j minus 1. Okay? This is the mapping that I have, okay? New coordinates as a function of the old coordinates. Okay? If I claim that this can be represented by a 2 by 2 matrix, will you accept that? If you don't, that's fine, because I'm going to use, because I'm typing it, I'm going to use vector notation like this. Okay, what is this? PT transpose, because I wrote a row vector, so transpose is just the column vector PT. Okay? I have, you agree with that? Oh, I forgot to close the parenthesis. It's some function of ij. Okay? What is the first component P? What function of ij is it? P equals, you're looking at the slide, right? P equals what?
I.
P equals I, right? So can you express that as a linear combination of I and j?
1, 0.
1, 0, right? So the first row of my transformation is 1, 0. The second row is what?
It's an affine combination.
It's an affine combination. So there's a constant. So we'll, we will either add a dimension, or we will worry about the constant, or we'll be sloppy with the notation.
So, but if we just take I plus j,
yeah, the
if we
linear
just
part
take
of it.
Yeah, 1, 1, 1, 1, 1.
So think of the matrix 1, 0, 1, 1. That's a 2 by 2 matrix, and it gives you the linear part of this affine transformation. 1, 0, 1, 1 times ij plus the constant vector 0, 1. Right?
Yes.
What is the inverse of t? This 2 by 2 matrix, can you invert it?
1, 0, minus 1, 1.
And that is exactly what I told you. In other words, what are you doing? You are given two equations, P equals I, T equals I plus J minus 1. Solve them for Ij in terms of Pt. That's the inverse. Right? So this is basically, if you go back and review your linear algebra, this is the kind of things you're doing. Nothing very deep, really. Okay, but it is, this is the machinery that you're using. Okay. All right. So let me continue then. So you have this inverse mapping. Okay. Now we want to determine the transformed iteration space. And then what we want to do is we want to write loops that traverse this new iteration space. And the outer loop must be the time. The inner loop is marked to be parallel. Okay. With a pragma. And we have to write the new loop body. Okay. So how many tasks do we have? One, what is the image of my original rectangle by this transformation ij goes to I comma I plus j minus 1. Okay? That is the first problem. That is, what is the transformed iteration space? Then we have to solve another problem, and that is, given an iteration space in the form of linear inequalities or vertices, whatever, you have given a polyhedron, you want to write a set of loops that visit all of these points in the polyhedron and nothing else other than the points in the polyhedron. So this is called the scanning of a polyhedron, scanning problem. And that was solved for the first time in 1990 by Irigoyen and sorry, not by Irigoyen and Trioli, but by Corinne Oncourt and Irigoyen. Okay. And then after you generate, you also have to modify the loop body. And we'll see exactly how to do this, okay? So what is the control structure? So here is, you have a source program. From it, you get the loop bounds. The loop bounds define the polyhedral set, okay? And that is what we call the iteration space in terms of the inequalities. You want to transform this iteration space to get a new set of inequalities. Then you want to get new loop bounds that visit this transformed iteration space. And then you produce the target, and you have to figure out how to do the loop body. Okay? All right. So you had for I equals 1 to n minus 1, j equals 1 to m minus 1, right? Let us write this as a set of constraints, ij, such that, I'm just writing the inequalities, right? Now this is the transform space. Okay, and here I am going to think of not the image of the polyhedron by some transformation. Okay, I'm going to actually go back a few slides and talk about this. Okay. You have this rectangle, just visualize this rectangle, and after this rectangle you have a parallelogram. Okay, you have a mapping that takes ij and gives me tp, and what I could do is I could take that mapping and apply it to all the 4 vertices, and I get the new vertices, right? And so these new vertices define my new iteration space. Okay? The problem is that I may not have the vertex representation of this polyhedron because I'm looking at loop bounds. The loop bounds give me the representation of this in terms of inequalities. I less than 0, j less than, I greater than or equal to 1, j greater than or equal to 1, I less than n, j less than m, right? These are linear inequalities. So how am I going to find the image of a polyhedron by some function like the one I just talked about? Okay, and here the dual representation and the inverse mapping is really very useful. Here's how you do it. Okay, this new set is the set of points such that if I apply the inverse to this, I end up in the rectangle. Do you agree with me? So this new domain, the image of this, the image of the original polyhedron by the function f or by the transformation t is the same as the set of points or the image by the inverse of this parallelogram, right? So it is the set of points such that if I apply the inverse map, I respect the constraints of the original. Is this very simple, intuitive idea clear to you? The image by a transformation T is the set of points such that when I apply T inverse to that point, I am in the rectangle or in the original, in the source. Okay. Let me pause for a bit, because this is, although it is a seemingly very simple idea, it has deep implications, because I will then, once you accept my statement, you will see very mechanically how the program is constructed, how the constraints of the new set is constructed. So, any questions about this claim?
So it was an transform plus a vector, which was like affine space.
Yeah, just think of it as some mapping, linear or affine.
Okay.
That doesn't
Okay.
matter. I'm mapping original space to new space.
Yeah.
Okay. Think of that as the transformation.
Okay.
You accept this, right? The image of a polyhedron P by transformation T is nothing but the set of points such that T inverse of Z, or applying T inverse to that set gets me the original polyhedron. Okay, that means the set of points Z such that T inverse Z respects all the constraints of the original polyhedron. Do you accept this? If you have any doubts, any questions about this, then I'm happy to repeat, and I'll no questions about this anymore, or no questions about this. This is it seems obvious, right? And it is obvious. It is just that when you take this view, it is very, very, very easy to construct that image. Okay. This is the beauty of what is called the dual representation. Okay. Now I'm going to tell you how I got from here to here. Okay. What did I do? See, this is the set of points ij such that they respect some constraints, right? The constraints of the rectangle. Its image by the mapping TP, okay, is the set of points such that, I'm calling the points P and T, such that when I apply T inverse to PT, the first coordinate can be replaced by I and the second by J. And so if you look at the constraints and don't look at the symbols or expressions, 1 less than or equal to first coordinate less than or equal to n minus 1. Okay, I apply the inverse mapping to PT, and I get 1 less than or equal to P, which is the first coordinate, less than or equal to n minus 1, and 1 less than or equal to T minus P plus 1 less than or equal to m minus 1. That means wherever I appears, I replace it by the first coordinate expression of the inverse applied to TP. Wherever J appears, I replace it by the second coordinate expression in the inverse. That's all I'm doing. Now I have to do a little bit of algebra to simplify, but that's all. Okay? So given a polyhedron and a transformation, what we do is we find its image by that transformation by really computing the inverse of that transformation and plugging it into the constraints of the original polyhedron. All right? So we have solved the first problem, which is how to figure out the constraints of the first, of the transformed iteration space. Okay, from there we want to get to loops. We want to visit all these points P and T in the order of P T outer, P inner, right? That is our goal. T is the outer loop, which represents time, and then the inner loop is the loop over P, which we are going to declare to be a parallel loop. Okay, so how do you do that? This is the answer. I haven't told you the algorithm yet, but when you do that, this is what you get. Okay. And then, later on during the tutorial, we have some exercises for you that make you walk through this. Okay. All right. So, how did I get this? Okay. The algorithm is a very beautiful algorithm developed by Fourier and Motzkin, or based on Fourier-Motzkin elimination, was developed by Ankur and Irigoyen. Okay. What you do is you have all these constraints, I less than or equal to P, J less than, so you have constraints on P and T and on some expressions involving P and T, okay? If you look at the constraints that involve P, so the algorithm works inner to outer, okay? I will figure out the bounds on the inner loop, the lower bound and the upper bound on the innermost loop first. Okay, how do I do that? So the inner loop that I desire is P. Okay, I look at all my constraints or inequalities involving P and T, and I look at the coefficient of P in that constraint and look at its sign. Okay, so the first constraint is 1 less than or equal to P. Okay, and I figure out whether this constraint gives me a lower bound or an upper bound expression on P. You can tell me that, right? The first constraint, 1 less than or equal to P. What do I get? Is that a lower bound on P or an upper bound on P? It says that P must be greater than or equal to something. So the expression 1 that is on the left-hand side of that constraint is a lower bound on P. Okay. The next constraint that involves P less than or equal to n minus 1. That the expression on the other side. So you basically take all these constraints and you manipulate so that the P term is on the one side and everything else is on the other side. So P less than or equal to n minus 1 is an upper bound on P. What about the next constraint? P less than or equal to T. Does that give you an upper bound or a lower bound on P? Any volunteers? P less than or equal to T. On the other side of the inequality, you have some expression. That expression is a lower bound on P or is it an upper bound on P? Is my question ambiguous or is it not clear?
It's upper bound.
I'm sorry?
It's upper bound.
It's an upper bound, right? That
Yeah.
expression, the right-hand side of that expression of that inequality is the expression T. In general, it is some AI, A times T plus B times whatever other indices plus maybe some function of N or M plus constant, etc. Right? All of that is some linear expression involving all the outer indices. Okay? That expression is an upper bound because on the left-hand side, you have taken P. If the coefficient of P was -3, let's say, okay, then when you write it, you want to write it such that, if it -3 times P, and you will see that in a little bit, okay? That basically means that the constraint would be written as p greater than or equal to t divided by 3. Because what you want is the variable p by itself, that index, and depending on its sign, the inequality changes less than or equal to or greater than or equal to. Okay? And based on that, therefore, the expression is either a lower bound or an upper bound. So here, this inequality p less than or equal to t is an upper bound expression, or gives me an upper bound expression on p. And now look at the fourth constraint, t less than or equal to m plus p minus 2. If you manipulate it, what do you get? T minus m plus 2 less than or equal to p. You want p by itself on one side of the inequality. Okay? And so if you rewrite that last constraint as t minus m plus 2 less than or equal to p, you find that t minus m plus 2 expression is a lower bound on p. Okay? And that's why you generate this loop, a for loop where p is greater than both the lower bounds. It's satisfying the and of those inequalities, and p is less than or equal to the min of the upper bounds. That is how you determine the bounds on the loop that visit p. Okay? This is the first step in this recursive algorithm. You work inside out. You know, I spent some time explaining this algorithm on the slide for this particular example because it is important. Now, if you look at it in the notation, you have basically, you have some variable Zn. Okay, Zn is your vector, which is the indices of the iteration space. Okay. For each inequality in this domain, right? Rearrange it into the form some coefficient an times Zn is greater than or equal to the expression for some constant coefficient an. If an is positive, then the expression divided by an is a lower bound on the index Zn. Okay? Otherwise, minus expression divided by an is an upper bound. Agree? Okay? So you have a polyhedral set that is defined by a number of inequalities. Each one is a set of coefficients. You know, it's a linear combination of the index names plus constant greater than or equal to 0. Okay? From each one of the constraints of the polyhedron, you will construct some lower bound expressions and some upper bound expressions. Okay? Let there be P lower bound expressions and Q upper bound expressions. The innermost loop that you generate, that is for Zn equals the max of all the lower bound expressions and the min of all the upper bound expressions. That is the termination of the loop, and Zn plus plus. Okay?